All right, welcome. My name's Asher Roll. I'm a sort of independent software developer and software architect in Brisbane in Australia. And today I'm going to speak a little bit about static initialization and how we can safely do it, not only in libraries but also in our main code. So we're going to cover a few topics, that will sort of build up an understanding of what it means to do static initialization, how the compiler actually builds it and does it, and from there we can come up with some useful patterns that you've probably seen before, and we'll start to understand how we can apply those in our libraries. And accompanying this this talk at this GitHub site, which I'll publish after the presentation, will be all the code in the presentation and a slightly better set out example project that you can start as a basis to work from if you want to experiment with these ideas. Right, so a few assumptions. I'm only really looking at C++ 17 and above. There's a few minor differences below that. I'm not going to be covering thread local storage, and I'm not going to be covering thread local variables and thread storage durations. We're just going to focus on mostly static storage. We're not going to cover runtime loading and unloadable shared libraries, although we will cover shared libraries. And I'm trying to strike a balance here between understanding and absolutely exact to the letter of the specification. It's more about building an understanding in your mind about what these things do and how they operate and how the compiler arranges this stuff to work for us. So that means that I am going to gloss over a few implementation details, but like I said, they're not going to be particularly relevant for developing the understanding and being able to use these techniques. So static initialization. So what we're really talking about here is a storage duration inside the running program. So we often will have global values that we want to use in our application, like a logger. We might have thread pools, we might have resource managers, we might have something that manages a GPU, and we want to be able to talk to those things from within our code without having to sort of pass down all this data through a huge object hierarchy and things like that. So as much as we kind of love to hate the singleton pattern or global state, sometimes it's actually really useful. And the C++ standard itself, this STL, actually uses a lot of these techniques, particularly around things like the stood in and stood out, C in, C out, and error and all that sort of stuff, and how that gets initialized. And a sort of a orthogonal, but not quite exactly the same sort of thing applies to if you have any third-party dependencies in your library. So if you're developing a library and you're using another third-party library inside your library, say curl or OpenSSL or anything like that, it also has initialization requirements, and quite often those are global to the program execution. So you're supposed to only initialize it once and destroy it once at program exit, not constantly open and close it. So we need to be able to find a way to manage that as well. So storage duration. So there's two orthogonal concepts here. There's storage duration and there's linkage. And both of them have this static keyword in them. So it's important to be able to pick apart the two. So storage duration is around how long the object lives, right? So you have automatic storage, so that's basically stuff allocated on the stack. Your typical, I'm not sure if I can point them out here, your typical, where are we? Variables inside a function declaration. That's static, that's automatic. Static duration are things that we declare in the global namespace. For instance, here we've got a local counter and a global counter. We've got things in the anonymous namespace that's equivalent to being static inside the translation unit. We can have static duration inside a namespace. We can also have static duration inside a function or a block, to be more precise. It could be inside an if block or a for loop or whatever. It's still within a block. We can have static duration in a template-based, in a class, and we can also inline declare this, and this is useful when you're putting a type within a header file which you're going to include in multiple places. And because we do the inline static there, we don't have to have an external declaration like we do here, and it just means that the compiler and linker sort out one and only one instance of that for us. So if we look again at this exact same set of code from a perspective of linkage, now we have different types of linkage. So where is this value accessible from? So there's no linkage, which means it's only available in the current scope. So if we look here, we've got that inside our functions. So both our automatic storage and our static storage, both no linkage because you can't access it from anywhere else. Whereas we might have internal linkage here because it's only available within the same translation unit, or we have external linkage here, which is available to other translation units. So everyone got that? It's kind of, there's lots of different little nuances here that we have to sort of plug together to make work. And again, there's another type which is, we have our no linkage here as well for our dynamic storage duration, which I forgot to say. So dynamic storage duration obviously is things we allocate on the heap. The tricky bit here is that the variable A is actually located on the stack. It's an automatic object, but the thing it points to is the object with dynamic duration, which you manage with new and delete, or preferably with a smart pointer or something like that. Okay. So we're going to go through a little bit of a detour. What happens when you load and run a program? So as part of this talk, we're going to delve probably a little bit deeper than some people have before. We're going to look at what the compiler generates and how it generates it, how it manages this storage duration stuff. Because once you understand that, you can sort of make the inference about why it is the way it is and the problems that you're likely to come across. So at a very simple sort of level, when we load a program, there's actually a multi-step process, right? We've got our program file, and it contains a bunch of what's called segments. So they're effectively named blocks that have different roles within our program. So we start with the kernel and the loader setting up our memory space. The loader then takes the program and places all the segments in memory at the right locations, does a bunch of linking. It establishes our heap and our stack. And so in general, our heap grows up and our stack grows down. That's just the sort of convention that's been developed over the years, and that's what the CPUs support. When our program's up and running, the loader then essentially jumps into the start routines. So this happens before main. So you may have seen the CRT0 or CRT1.0 files, somewhere like that. That's a compiler-provided startup routine. It's generally written in assembly, and it's very much platform-specific. And its job is to get everything else ready for your program to operate. So in this case, what it will do is it will load our data segments, it will do linking, and then it jumps into start, and it runs our initialization routines. So all our initialization routines are where we start to get our static storage duration stuff initialized. Right? It then calls our main function, and when our main finishes, it then goes and calls a whole bunch of finalizers that clean up all of our static stuff. So when we load the program file, the segments are all put into place. There's a special segment we're going to see a bit more. It's called BSS. The name comes from our arcane traditions of older compiler generators, but let's just call it BSS. And essentially that's a special segment that's kind of, the program says, hey, I need you to allocate me a block of this many zeros, right? And that becomes a BSS segment. It just means you don't need to store it in the program file itself. We just store a thing that says, hey, I need 10K worth of zeros over here, please. It's just a shortcut so we don't have to have big empty holes in our files. Okay, so non-local variables, these are the ones that are scoped at the file scope, in a namespace scope or the global scope, things like that. It can be class or struct level objects, values. So to be clear, they have static storage duration, which means they live for the duration of the program. They have internal or external linkage, which means Either they're only available in that one translation unit, i.e. they're prefixed with static or they're in an anonymous namespace, or they have external linkage, which means other translation units can get access to that object, can get access to that variable. Now, these are normally mapped into the .data segment. So .data segment is just a bunch of bytes that's sitting in your program space with pre-initialized variables, essentially, ready for the program to start executing. There's also a RO data for read-only data. So if you happen to have const static objects, they'll probably go into RO data. There's somewhat platform dependent, especially in the embedded world, that might actually go to a totally different set of memory that isn't writable. It might be in your program flash storage rather than a RAM sort of location. And if they're zero initialized, which we'll get onto later, they'll be sort of pushed into the BSS segment rather than allocating storage for them in the program itself. Local variables of static storage duration. So these are your block scope static variables. So again, they have static storage duration, it's in the name, and they have no linkage. Whoops, wrong buttons. Wrong buttons, yay, sorry. All right, sorry about that. The fun part of these things is, again, they're mapped into data, RO data, or BSS, depending on how they're initialized, and we'll get into exactly what that means in a minute. So in principle, they're initialized on the first time control flow passes that variable declaration, and we'll see some code in a second. However, that means that you can't predict necessarily exactly when they're going to be initialized in your program. It's going to be the first time that block is entered, essentially. So the compiler has to therefore make sure that that initialization is thread safe. Only one thread can initialize it at a time, and everything else has to wait until it's initialized. And it has a minor cost associated with each time that control passes through that block. It's got to check, has this been initialized? If so, then it's cool, I can use it. If not, I have to go and initialize it, and then I can use it. The compiler is allowed to move that initialization before the program starts, i.e. before main is called. So at the same time as your sort of non-local storage, static storage duration stuff is initialized. In some cases, it can do that. We'll get into a few in a minute. So in the standard, there's quite a dense bit of text about what all these initialization phases are and how they work and what you can and can't rely on. And it's hard to decode. So I'm hoping I'm going to do a reasonable job of explaining it, enough to give you a good intuition. So there's three main phases. There's static initialization, dynamic initialization, and the initialization for those static local variables, which is kind of separate. That happens during the runtime normally. Static initialization is broken into constants and zero initialization. And you might be able to guess which segments they go into. So constant initialization, if the compiler can tell what the value of a variable or an object is, what its memory representation is, it'll just store that in the data segment ready for you to use. So there's zero cost to initialize it because it's already initialized by the time it's loaded into memory. And that's normally done in the data segment or the read-only data segment if it's a constant. Zero initialization is similar, except if the compile time value is known to be basically zeros, so that might be a null pointer, it might be a default initialized integer of 0 or something like that, it'll just put it in the BSS segment to save having to write it into the program file. Dynamic initialization is everything else. So if it's not a fixed value, or it can't determine what that fixed value is at compile time, then we start triggering this dynamic initialization phase at the beginning before main. And what that means is it places the variable into BSS, so it's going to be loaded at the beginning with a value of 0, and then it's going to organize dynamic initialization code to be run during that startup phase before main is called, and we'll see how that operates in a minute. However, this is where the main problems with static initialization come in and the so-called static order, initialization order fiasco, right, is because ordering is a bit complicated here, and this is a very brief summary of it, but basically there's unordered sections, so you can't really predict the ordering of a class template static member initialization, because it may not actually have been initialized in your file. It might be initialized in a different user of that file, and it's going to depend on ordering those files and all sorts of things. Partially ordered things like inline static variables, if and only if they're always consistently initialized in order in every translation unit. It's, like I said, I'm trying to keep this brief because honestly, my hot take here is make sure you don't do it, because that's what breaks everything. Right? So, and the other stage is ordering. We can rely on ordering of static variables within a translation unit. So they happen in declaration order. And we'll see why that happens in a minute. Okay, so static local variables. And now the standard states that the initialization of these has to strongly happen before they're first accessed. But it doesn't have to be inline in the function. It could actually happen before main is called. It's up to the implementations to work out what they want to do. So in all the implementations that I've looked at, which is basically GCC and Clang, because of what I've been using, it always happens as control passes through, unless they were constant initialized or zero initialized, which we'll look at a little bit later as well. So what really happens, as I said, first time control passes through the function, that's when the initialization step happens. That's when some locking occurs. That's when the compiler arranges for those things to happen. So we're going to look at some of the implementation here. So it's not like I'm going to show some assembly that's generated out of some fairly simple code, and we'll use that to kind of understand what's going on. It's not important to understand the assembly. I'll just walk you through what the various directives actually tell the assembler to do. So constant initialization is pretty simple, as you might expect. If we have a global counter or a internal or external linkage static duration objects, they all go into the data segment. So this directive data tells it, hey, when you're emitting stuff, put it into the data segment, please. And so we say we've got a global counter. It's a long, which in assembly speak means it's a 32-bit value. And its value is 10. And there's another one, local counter, which is, again, a long, 32-bit integer, and its value is 11. So we can see our values here that it's loaded. The interesting thing here is this global directive here means that this symbol here is actually available outside of this translation unit. So it marks it as a symbol that gets written into a table in the magic guts of all the object file representations. So that's pretty straightforward, I hope. Zero initialization is similar but different enough to warrant looking at. So again, all of these options here are zero initialized. This is a default initialization, which means an integer gets a zero. Obviously, it's a big explicit one. Default initialization of a pointer is, again, null or zero, and the same for specifically setting it. So in this case, again, we're exporting all of these symbols. We start in the BSS segment, which means all of these go into the magic zero segment, which we don't need to store, but we're going to allocate anyway. And in this case, in GCC, it uses a zero directive, which says, I want to allocate 8 0 bytes, please. So a 64-bit integer, and because these are pointers here. And you'll note that it's reordered this. And it's probably ordered by alignment, but the compiler can make any choice at once, because really it doesn't matter, because this is all set up before your program runs. So there is no initialization order here. It's just they're all initialized at the same time. Okay, so dynamic initialization. This is where it starts to get a little bit more interesting. If we force these static storage duration objects to have dynamic initialization by making them depend on some other thing that the compiler doesn't know the value of, then it's got to say, well, I can't compute that at compile time, so I'm going to have to defer that to runtime to work out what the value is going to be. And to do that, it's got to play some tricks. So first of all, we see our global values here, again, both exported, both in the BSS segment. In this case, clang is using long and setting the value to 0. So it's exactly the same as the 0 directive. It's just clang prefers to use that, and GCC prefers to use .0. Now, it creates, the compiler, this function here. And this function contains the code required to initialize our variables. So you'll see it's reading the external integer here, and it's putting them into our two values here at runtime. So how does this get called? Well, there's a special segment called initArray. And what this is a collection of effectively pointers to these functions that the linker will join together all at the end. And that's what our startup routine uses to go and initialize everything. It calls all of these functions in whatever order they appear. And that gives you the opportunity then to dynamically calculate all these things before main runs. Any questions about that so far? Please just yell out if you have any questions, or if I'm speaking too fast. I'm Australian, I tend to speak very quickly and skip syllables and words. All right, so quick detour on linking. We know that our CPP files generate object files, and those object files get linked together into our program. So what's actually happening here is all of the segments of the same type are joined together and concatenated by the linker and put into our program, ready for the loader to extract and put out. And this is where the ordering issues come in, because we can't always predict the order that our object files are going to be linked. And effectively, that's up to, it's not random, but it comes down to what order they're specified on in the linker command line arguments. And it could be which libraries are included first, because sometimes if you swap a library, a linkage of a library before a different one, or an object file before this, you will change the order in the file of all of these things, and especially the values in the init array. And that's why we can't rely on the dynamic initialization ordering, is because we can't actually predict that ordering. Is because the linker's just gone, yeah, there's a bunch of numbers, I'll just concatenate them all together and you can deal with that later. So let's have a little bit more look into how that init array works. So this is obviously an artist's impression of the code. It's actually normally written in assembly, but I thought I'd translate it into something we understand to talk through it. The implementation is generally provided by the compiler, and what it does is runs all the initializers in the init array, calls main, and the order of all those things is obviously fragile, as I said before. We can't necessarily predict it. So if we look here, we've got a function pointer that takes a void and returns a void. So it's basically just a very simple function. None of those initialization functions take any arguments. They're just, what do I do right now, right? The linker actually generates a couple of symbols for us to note where in memory the start and the stop of that array is going to be. So if we conceptually think about setting it up, we can just treat that like a span. It'll just go through that span, call each of the functions. Then it'll call our main. All right. Now, we'll see this in a minute, but when you run some of these initialization functions, if they need to register destructors or anything like that, they will get queued into what's called the @exit list. So essentially, it's a list that gets built as your program sets everything up, and at the end of execution, it'll basically go through that list backwards and call all the destruction routines. So this is how you get the ordering of initialization and then the ordering of destruction in whatever scope you're in, the block scope, in the files, all that sort of thing. So does anyone have any questions about this? So if we were to write our own exit function, it's think of it like a vector of those function pointers, and we just push them onto that list as the calls come in. We'll see some of these calls in place in a second, but I just wanted to establish that. Right. Now, if we look at static local variables, again, constant initialization looks kind of the same as you would expect from anything else. If the compiler knows it at runtime, so if it might be 42 or it might be 0, then we're just going to, in this case, our implementation of our function here in the text segment, which is where our code goes. We have our get constant function as a global. It's implemented by just loading the value and returning it. So we actually have the value stored in the data segment, and it's pre-initialized to the value 42, which is what we specified here. Or if we were to put 0, then this would become the BSS segment, and we would just get 0 stored. It's pretty straightforward. The dynamic initialization, this is where it gets much nastier. In this case, our get dynamic function now has to do a few things. Here it is checking, sorry, let's go down here first. So we've got our storage for our symbol, our static dynamic variable here. We've got a guard object. Now, the compiler is allocating 8 bytes, so a 64-bit value here, and it's allocating our integer here. So what happens is it does a double check lock. So it will go and read the guard and test if one of the bytes is set, because it only really uses one of the bytes, but it still puts it in a 64-bit chunk, probably to do with cache coherency and false sharing and things. It's up to the compiler to determine. But so here it is testing it. If it's already been initialized, then it can just return it. If it hasn't been initialized, it comes down here and it starts doing this guard acquire thing. So this is effectively a global mutex. He says, hey, I want to acquire this guard, and I want to then, once I've got that, I check again to see if I've been initialized yet. Yeah.
Do you know if it's possible to make the compiler not call libatomic on this, but inline the atomic instructions? Because all it is like acquire, check with an acquire variable.
It's actually more complicated if you go and look at the implementations. They actually do a bunch of other stuff in these things, but this is just what the compiler is generating. So I don't know if you can make it better. But what it comes down to is that only happens in the first time you go through the loop anyway, right? So you're always going to pay the cost for this initial check. So it's always going to do the first test when you run through that thing to check, hey, is my value initialized? If it isn't initialized, then I have to go and initialize it. To safely do the initialization, I do this lock, double check that it hasn't been initialized, and if it hasn't been, then I initialize it and release the lock, and then I return the value. So the first time through, you're going to run this expensive code, which probably involves a global mutex for all threads, which is fun, but it's the first time you run it. Every other time, it's just going to be a simple test of a memory location. So yes, this has some hidden cost. Any other questions on that? It's somewhat complicated assembly code to try and read through, but I just wanted to give you the sort of feeling for what's going on. Okay, now what happens, so that was all integers. That was very boring, right? So what happens if we have constructors into the mix? Let's have a look. So we're going to create a very simple structure with a constructor and a destructor and create a static instance of it. So we get the familiar initializer. In this case, it calls the constructor, and then here is the bit that registers our destructor with @exit. So the std @exit just really compiles down to this other C library provided function for us. Again, we just have a location for it, has to have a unique address, and then we queue up our initializer into the init array. Right, so what happens, what that means is we come along in dynamic initialization, call our constructor, register our destructor, and then move on with the next initialization. And so remember, those destructors that get registered in @exit are done in reverse order when we're shutting down. Okay, well, it becomes important in a second. So what does that mean? Constant and zero initialization is predictable and reliable, and we should be trying to use that wherever possible for our sort of static variables, static storage durations. Dynamic initialization is much worse. It's really hard to predict what's going to happen and when. And you might have it working now, but then you might, 6 months' time, you might make a minor change somewhere and reorder something, or another developer comes in and changes something, and now all of a sudden you've got a problem that you didn't have before, the code looks like it should still work, but you can't really be sure unless you test it completely, and that's hard. So basically, this is why we have this so-called static order initialization fiasco, or static initialization order fiasco. And funnily enough, my day job involves C#, and I ran into exactly this whilst I was writing this talk, and I beat my head against the wall for 5 minutes trying to work out what was going on, and I realised, oh no, they have exactly the same problem. So it's not just C++, it's other languages too that have sort of the concept of static storage have exactly the same problem. Okay, so let's have a talk about some common initialization patterns you've probably seen. So the first one is the Mayer singleton. So this is, and then we'll look at a nifty counter and another thing which is a sort of a static buffer and a global reference, which also uses a nifty counter as well. So Mayer singleton, it's a pretty standard pattern you've probably seen. It's essentially, one of these local statics and a getter, so it's initialized the first use. It could be in a class or it could be a function. Doesn't matter. Same thing. So what happens if we have dependencies between our Mayer singletons? So if we have a log singleton and we have some other singleton that uses the log, right? That all works fine, surely, right? So we initialize it, we get the right logging, everything happens, everything's happy, right? What happens if we delete this line where we call the log here? We get an out of order. We get a use after free because the log was destroyed before the singleton was destroyed. And the reason that happens is, well, it worked before because before singleton was completed construction, it talked to the log, which completed construction, so it registered its destructor before the singleton's destructor. But when we didn't call this log function here, the singleton constructed, then the log constructed, which means the log is destroyed before the singleton is destroyed. So the Mayer singleton is great as long as you don't have any dependencies between your singletons. Okay. Nifty counter. So this allows us to control when we actually run the initialization code. And it's done by injecting an object with internal linkage into every translation unit that uses this object. And we use that injected object's constructor and destructor to manage the lifetime of whatever it is we're managing. So again, this is an example of this in common use is IOStream. This is how this gets initialized, how your C in and C out gets initialized before your program runs. So for nifty counter example, if we just have a simple counter here in an instance, and say we want to have a global resource which is some vector events, just as an arbitrary type, as an example. So obviously we use it by including the nifty counter thing, and we can access our vector. Because at this point we've included this object which has been initialized before our code can run. It's been registered as a static storage duration initialization in this file and in fact in every single file that uses it. So over in the implementation we have an instance count and whatever the thing is we're actually trying to manage. On the construction, if we were 0 we create it. On the destruction, if we get down to 0 we delete it. It's pretty straightforward. Is that everyone cool with that? Yeah. Static buffer. Yeah.
That doesn't help you with the destruction order if you have two of these depending on each other. And
don't have dependencies. Is what it comes down to. So this only allows you to know that you're the first initialization, and therefore you can do. Sorry, you're the first call to the initialization in your program, and if you're the last call to the destructor, it means you know you can clean up.
Yeah, but
That's,
two of these depending on each other still.
You have no guarantees.
Okay.
This is why dependencies between singletons are a bad idea, and we'll see some techniques later on to help mitigate that. So another modification of that is we might have a static buffer and a reference. So in this case, it's just like the nifty counter. We still have a counter. We have our log object. here. And what we're doing is, again, we have a counter, we're allocating the storage of the correct size and alignment for our object into a buffer that becomes uninitialized. And then we're creating a reference to the beginning of that buffer, which is where our object will be, but isn't yet, which is dubious, but works. And then, obviously, we just placement new the object into that buffer, and we destroy it when our nifty counter wants to clean up. So that's essentially what happens in the cout, cin code in your standard library. Yay. Seems to be coming back. Yeah, apparently I'm done. I've got the big hook, get off the stage. Just waiting for the projector to come back on. Yeah. Correct, yeah. Or maybe we got crowd-striked or something. Maybe. Maybe the projector doesn't like... Hey, and we're back. So what were we saying? Yes, so again, nope. Yep, maybe. Let's move on. It obviously doesn't like this slide. So linking and loading libraries. What does the standard say about it? Well, basically nothing. It's all implementation defined, which is fun, but also means we have to be careful about what we rely on to make this work. So there's a lot of common ways that this is all done, and they're kind of settled on the same patterns in most platforms. Embedded systems, perhaps you don't have dynamically loaded libraries, but it's the same sort of processes in most operating systems. So we have statically linked libraries, which are effectively just a collection of object files jammed together in an archive. That's all they are. So essentially, when you're linking against a static library, it's just grabbing all those objects and adding them into the mix for the linker. So that means all your BSS and your data and your init array and everything like that all gets chunked in together. Shared libraries are kind of the same, except now we have the program loader being responsible for taking them off disk, loading them into space, linking up certain parts of all the symbols and stuff so that everything can find each other. And again, because it's implementation defined, the compiler must ensure that it's as if it was all running in the abstract machine. The same state is set up before your program runs. So there are platform-specific ways to get initialization, but be warned, this is well beyond the standard, and this is going to potentially be troublesome to manage. So in Linux, there's constructor and destructor attributes you can use on functions, which essentially register them like constructors and destructors in C++. There's also an init and a fini method that are technically deprecated, but probably will never disappear. In Windows, there's something similar. I'm just not as familiar with it. I do know that there's a DLL main function that gets called by the loader when processes and threads attach and detach and things like that. So you can register functions and do operations in there. Again, this is fairly advanced territory, and you really got to know what's going on to make use of this because you're well outside the standard at this point. So library static initialization. How can we, knowing what we now know, how can we get this right? Well, we can rely on zeros, we can rely on constants. Let's not rely on dynamic initialization because that makes our life hard and unpredictable. We can rely on the order of initialization in a translation unit. We can rely on a nifty counter. We can rely on Maya singletons without any dependencies between them. We can rely on class member initialization order. That's very handy, turns out. So let's have a look at some ideas. The first one is the simplest one. It's what's been done for decades, and most C libraries do this. You have some sort of start and stop, initialization, finalize sort of function calls that you rely on the client code to call in your library. So curl does this, OpenSSL does this, all those sort of libraries do it. So pretty straightforward. Problem is it's easy to forget to call one or both. You're going to get runtime errors pretty easily if you don't. What happens if you call it multiple times? You've got to read the documentation to specify it. Right? Idea 2, we can use a nifty counter to initialize our library. So we can have in our main header, we can have a little nifty counter and say, right, the first translation unit gets to call the init function, the last and register its destructor. Again, same sort of problems. Tricky to inject configuration, which might be a thing for your library. You might want to take parameters when you're configuring your objects in your library. We could have one singleton to rule them all. Again, nothing for the client to do. They just call functions, and we go off and create a singleton on the first use. Container classes, you can order dependencies between them inside that singleton. So if you've got multiple singleton things, that container object can control their lifetimes and order using the class member initialization orders. We lack precise control on timing of when that's going to occur, because it's going to be down to when it's injected into that init array. Pretty hard. Oops, sorry. Oh, I've done it again. And it's pretty hard to inject configuration into that, because there's nothing available from the outside world to put configuration in. So you're going to have some other function, your register configuration, which then now you're in this loop of, well, what gets initialized first. And the downside is you're going to end up coupling many parts of your library, if it's sufficiently complicated, into one translation unit that contains all of these things for your singleton object. So that can affect compile times. Idea 4, which is what I like, is we create a library handle using RARI. And the lifetime of that object manages the lifetime of our static scope within our library. So we force the client to make sure they have non-overlapping instances of it. So they could choose to have one for the lifetime of their program, or they could create it, destroy it, create it, destroy it, create it, destroy it as many times as they want, and it should all still work fine. We do need to watch out for objects being returned. Like if they end the lifetime of that handle, that object may no longer be valid. So but that's something for every API anyway. Again, we do have the problem of potentially coupling multiple parts of the library to one translation unit, but we can kind of mitigate that with using Pimple sort of compiler firewalls, so pointer to implementation stuff, to sort of hide the details away. And we can nest that too. So what I've created is a imaginatively named library. I think actually that should be called libexample. So the code for this will be available in this repo, probably sometime later this afternoon. It uses an RAI object a handle basically to manage the lifetime of all the objects that I create in my library. It uses a nifty counter for one-time initialization for external dependencies like curl or OpenSSL or anything like that. It uses Pimple the Pimple idiom to firewall off the library implementation details from the exposed header for the public interface, and it separates lifetime management of our static storage duration objects from their access. And we'll show you how we do that. So this is what we're trying to achieve, although that's probably not very well readable. The init routine comes in, initializes our nifty counter, we initialize our external dependencies, and at the end of main, it'll come and deinitialize our Nifty counter and clean up our external dependencies. In the application, we can create our handle, and it'll initialize our state. We can use the state as many times as we want, and we'll clean up our state when we destroy that handle. That's the object. So as a trivial example, we'll have a worker thread, pulls work off of a queue. There's a logger that the thread uses and most of the library uses. There's a queue and a worker object implementation. Go and have a look at the code if you're interested. It's pretty straightforward, not particularly efficient, but it works for this example. So if we have a look at our RAII object, we declare our implementation just as a forward declaration, and our API here. We have a constructor and a destructor. We disable move and copy. That's a choice, but for me that makes sense because you don't want a client library to accidentally make multiple copies of this object or move this object around. Moving probably not as bad, but in this particular case, but copying it definitely bad. Because what do you do with the unique pointer for your pimple? We then have, if they wanted to have multiple copies or handles to that thing, then they should store it in a shared pointer or something like that and pass that around. Again, we'll just have a pretend API, do some work with a message. Implementation-wise, we make our implementation, and we just have some little helper text here to when you run, if you build the project, it'll actually run through a very simple test suite in main to create one, call some functions, destroy it, try to create multiple ones, things like that. And obviously, we just forward on the work to the implementation. So our implementation is where we start to see some detail. So again, constructor, destructor, implementation, move, copy, elision. And this is important to disable move and copy in this case because this object here is going to own our static storage duration objects. It's going to manage its lifetime, or you could have multiple ones. So in this case, we have an instance lock as the first member. So that instance lock's job is to check, hey, are there any other copies of this thing in existence? Has another thread created one? And if it has, it'll throw an exception, which means none of these things will get initialized. They'll be left alone. And if you were to accidentally initialize multiple ones of these, you could affect a previous an existing instance that's running happily if you try to construct another one. So we basically abort out here quickly. And the reason, and we're using that as a member variable for just that reason, because you throw the exception there, the unwind process eventually ignores the construction of anything else below it. So whereas if it was a function that checked after you'd finished construction, you'd have blown away the state in our static data, which we'll see how that works in a minute. Again, we can pass member initialization. We can pass stuff between members in order to say, we construct the queue, we give the worker the access to the consumer for the queue so it can do its job. Pretty standard stuff. The log here just forwards on any stuff here to the implementation of this T, which happens to be our logger, which we'll see in a second. So ensuring we've got a single active handle, it's just effectively an object that has a atomic bool. Now, what I've started doing, and I like doing, is constant init is great for static storage duration objects. It forces the compiler to tell you if you're doing dynamic initialization. It's a compile error. So if you can put constant init there, you're safe because it's either constant initialization or it's zero initialization, which means you're good to go. It's a nice trick if you can use C++ 20 or above. Again, the instance lock, it's just checking, hey, does one already exist? And if it does, throw an exception. Otherwise, we're good to go. And on the destruction, so after this point, oops, I've done it again. After this point here has succeeded, after this, we know that everything running here is in a single thread because only one thread can gain access to that through that gate. So the good thing is once we've established that we are the only thread doing this initialization, we don't have to worry too much in here because we know there's only one thread running through it. So separating our lifetime from our access, we're going to create this object called a scope singleton, and its job is to maintain the lifetime of an instance and have a global static storage duration pointer to it. So all it does, on creation, it'll just double check that there's not one already active, and that's more of a programming your library problem, because you could effectively declare one of these objects in a different location in your library, and it would collide with the actual one you're expecting. So it's just a safety thing. We obviously have to disable this move and copy. I just haven't put the code in there because this instance here, the location of this instance is what is pointed to. So in our constructor, we assign the static storage duration pointer to our instance, and on the destruction, we basically remove it. So to access that, we might have a logger class like this. We obviously forward in our parameters into our constructor, and then rather than having to write scope singleton logger instance everywhere, we might just wrap it with some nice little convenience functions, because this scope instance access here just compiles down to a pointer dereference. One-time initialization, so if we have our external libraries, we can do a nifty counter. I'm trying to run through this because I'm about to run out of time. Again, standard nifty counter sort of setup that we have here, except instead of construction or destruction or anything like that, we can just call a convenience function that might go and run all our library initializers and code. And from the client call site, it just looks like this. We create an instance, the lifetime begins, we do our work, the lifetime ends. Or we could, if we misuse it, we create an instance here, do some work, create another instance or in another thread or anything like that, and we'll get an exception. And that's pretty much the way I like to handle the static initialization in libraries. Other things in the project you can look for, I've got a bit of code that verifies that the header file and the library that you're talking to, maybe if it's dynamically linked, are actually from the same version of the code. So just a little helper to help with that. And it's a little CMake project that does Clang, GCC, static, and dynamic shared libraries as part of the output. And it ensures, this is a key thing here, when you're building these libraries, make sure you hide all your symbols by default. Because otherwise, all of these carefully hidden objects in your library here can actually become accessible, and someone can link against it if they try hard enough. And that's basically that. So thank you. Any questions? Yeah. Hello.
So about order of initializations that you talked about, I wonder, is there any difference between context pair variables or context pair fields than regular cons?
No, because basically the context just means it's evaluated at, or can be evaluated at compile time. But where you store that is going to then have a static storage duration. So the compiler's pre-computed the value, stored it into the thing, so it's effectively constant initialization. If you were to have an object that has a context constructor, for instance, it would store the pre-computed state of that object, and then it might register the destructor as well. So it gets called just like using that @exit function. So, but essentially it's the same as assigning 10 to an integer.
Well, I just want to make a comment on this. There is a slight difference in const expers depending on whether it's ODR used or not ODR used.
Yeah.
If it's not ODR used, it actually doesn't have to have a location at all.
Yeah, doesn't exist.
The compiler could just paste it everywhere you use it. If it is ODR used, everything you said applies.
Yeah. Yeah. Thank you for the clarification. That's a good one. I will get this code up to the GitHub repo sometime soon. Yeah.
Just wondering, does link time optimization affect anything you presented?
That's a good question. I'm not sure. I think what you'll find is link time optimization will kind of maybe eliminate some stuff that it doesn't need, but I don't think it's going to change the way the the static initialization happens, it might move the initialization order around for you in an unpredictable way. But and again, it comes down to don't use dynamic initialization if you can get away with it. Anybody else? No? Well, thank you very much, and enjoy the rest of CppNorth.